Magnetars are rare, hypermagnetized neutron stars with magnetic fields so intense they can twist atomic structures and fracture their own crusts. Born from the collapse of massive stars, these exotic objects condense more than the Sun's mass into a sphere just 20 kilometers wide. But what truly sets them apart is their magnetic power, reaching strengths of -0 to the power 1 Gauss, capable of distorting space, generating gamma-ray flares, and triggering starquakes. These events can release more energy in a split second than the Sun emits over 100,000 years. Most magnetars rotate rapidly at birth and spin down quickly due to magnetic braking. Their short lifespans, less than 100,000 years, make them fleeting beacons in the universe. Yet they may explain some of the most mysterious cosmic events like fast radio bursts. Despite only a few dozen known magnetars, their physics challenges the limits of quantum theory, gravity, and particle behavior under extreme magnetic pressure. True or false? Magnetars are formed from white dwarfs that gain magnetic fields over time. False. Magnetars are formed from the core collapse of massive stars, not white dwarfs. They are a subtype of neutron star born with extremely high magnetic fields. What gives a magnetar its extreme magnetic field? Rapid rotation and turbulent dynamo during formation. Fill in the blank. Magnetars are a rare type of blank star. Neutron star. Fill in the blank. A magnetar's magnetic field can reach strengths of over blank Gauss. (10 to the 15 Gauss). How do magnetars lose energy over time? Via magnetic braking and flare activity. Fill in the blank. Sudden, violent shifts in a magnetar's crust are called blank. Starquakes. True or false? Magnetars emit continuous radiation rather than sudden bursts. False. Magnetars are known for sporadic, violent outbursts of high-energy radiation, often caused by crustal fractures or magnetic reconfigurations. Fill in the blank. The rapid loss of rotational energy in a magnetar is due to blank. Magnetic braking. Magnetic braking. Which of the following best describes a starquake? A cracking of a magnetar's crust from magnetic stress. Fill in the blank. Only about blank magnetars have been confirmed in our galaxy. "24. True or false? The magnetic field of a magnetar is strong enough to distort atomic orbitals. True. Fill in the blank. One of the most energetic magnetar flares occurred in blank and was detectable from across the galaxy. "2004. Why are magnetars thought to be linked to fast radio bursts, FRBs? They emit powerful, millisecond-scale radio bursts. Fill in the blank. The magnetic field of a magnetar decays over a period of about blank years. $10,000 to $100,000 years. Fill in the blank. Magnetars are born from the explosive death of a blank. Massive star. How do magnetars challenge our current understanding of quantum physics? And what implications do their magnetic fields have for theories of matter under extreme conditions? Magnetars challenge physics by creating magnetic fields so strong, up to 10 to the 15 Gauss, that they alter quantum processes. These fields can distort atomic structures, trigger vacuum birefringence, and affect the energy levels of particles, pushing quantum electrodynamics to its limits. The extreme pressure and density may also influence the internal composition of matter, offering clues about exotic states like quark-gluon plasma or hyperon-rich cores. Because their environments combine high gravity, intense magnetism, and extreme density, magnetars act as natural testbeds for studying how matter behaves under conditions where quantum theory, relativity, and nuclear physics intersect, something no Earth-based experiment can replicate. True or false? The magnetic pressure on a magnetar surface can exceed the gravitational pressure pulling inward. True. Which theoretical quantum effect has been observed near magnetars? Vacuum birefringence. Fill in the blank. The extreme magnetism of a magnetar causes the vacuum around it to behave like a blank. Polarized lens. A magnetar is spinning at 100 revolutions per second, but slows down by 1 revolution per second every 10 years due to magnetic braking. How long until it spins down to 10 revolutions per second? A magnetar begins spinning at 100 revolutions per second and slows down by 1 revolution every 10 years. To reach 10 revolutions per second, it must lose 90. We multiply 90 by 10, giving us a total of 900 years for this slowdown. What happens to atomic structures in a magnetar's magnetic field? They become elongated along magnetic field lines. A burst from a magnetar travels at light speed and is detected on Earth 50,000 light years away. How far did the energy travel in kilometers? To calculate how far a magnetar burst traveled, we use the formula. Distance equals number of light years multiplied by the number of kilometers in 1 light year. We're told the burst traveled 50,000 light years. 1 light year equals 9.461 times 10 to the 12 kilometers. Multiplying 50,000 by 9.461 times 10 to the 12 gives us approximately 4.73 times 10 to the 17 kilometers. True or false? Magnetars are theorized to form from binary star systems with black holes. False. Magnetars are formed from the collapse of solitary massive stars. Binary interactions may affect spin or mass loss, but they are not required for magnetar formation. Fill in the blank. The magnetic field lines of a magnetar are anchored in its blank. Crust. Why might magnetars emit gravitational waves? Due to non-spherical deformations in their crust. Fill in the blank. The power released by a single magnetar flare can equal the sun's output over blank. $100,000 years. True or false? The interior of a magnetar may contain exotic matter, such as deconfined quarks or superfluids. True. Fill in the blank. The loss of rotational energy due to magnetic braking is converted into blank. Electromagnetic radiation. What role does magnetic braking play in a magnetar's evolution? It slows down its rotation dramatically. A particle accelerated near a magnetar moves 1.2 times 10 to the 14 kilometers in 4,000 seconds. What is its average speed? To find the average speed of a particle near a magnetar, we divide the total distance by the time taken. The particle travels 1.2 times 10 to the 14 kilometers in 4,000 seconds. Dividing 1.2 times 10 to the 14 by 4.0 times 10 to the 3 gives us a speed of 3.0 times 10 to the 10 kilometers per second. How did you do? Tell us in the comments below. And thanks for watching BrainyKidz. We hope you had fun learning today. Don't forget to like, subscribe, and hit the bell so you never miss a new quiz. See you next time, Brainy friends.